Okay. Excellent. Let's continue. So the main aim of today's lecture is to discuss, to complete our discussion of this, of supersymmetry on a sigma model on a general target space. Then to turn on a potential and to discuss Morse theory, or the Morse inequality. But before that, I wanted to take a small diversion to address a question that Shoaib asked me yesterday, and it turns out it will also be relevant to today's lecture. So Shoaib asked me the following question. He asked me, when we got this exact solution for the first model we studied, just the supersymmetric quantum mechanics, it was an exact solution. The question he asked was, can we figure out what linear combination of the approximate perturbative solutions it was? And can we try to understand why it was that? Okay? And the answer is yes, and I'm going to sort of at least roughly indicate to you how we can do this. So let's work in an let's work with, for instance, a potential that looks something like this. A potential W that looks schematically like x plus x cube. Or maybe we want to minus x, so that cuts the axis, plus x cube. Okay? We will change the details of this potential as we go along, but just so that the cuttings with the real axis are like this. So there are three cuttings, and then there is something non-trivial to ask. Okay? The question was, we had the exact energy eigenstate. Hi, Nick. Yeah. So we have the exact energy eigenstate of this thing, but we also had done a perturbative analysis, a semi-classical analysis. Okay? And the exact eigenstate then gives us some linear combination. There's some sense in which it gives us some linear combination of the perturbative eigenstates. Okay? So first, can we work out what that linear combination is? And second, can we figure out why? From perturbative analysis. Okay? So let us recall that in this situation now I'll need your help. Anyone who has good notes, our exact wave function was it integral w of x dx sigma 3, was this right? By h bar psi naught. Right? And this was a way, we've chosen this so that w goes to infinity, at positive infinity. We want this to converge, so sigma 3 should be minus 1. So we choose psi naught to be 0, 1, the downstate. Okay? And in this situation, we had perturbative analysis where this was a downstate, this was a downstate, this was an upstate. In our perturbation theory, we got states localized around here, and around here. Okay? And so the first question is, what linear combination of these three things is it? Just let's read it off from the answer. And later try to figure out why. Okay? So, you see, the part that is going to produce, see, let's look at this W here. This W in this neighborhood, say there's some x naught, in this case it's 1, but we don't want to fix to such details. There's some x naught, in this case it happens to be 1 for this choice, where W has crossed this axis. Okay, in the neighborhood of x naught, this W here was some alpha x minus x naught. right? Now, alpha is the harmonic oscillator potential, harmonic oscillator frequency at that point. Okay, so this thing here, in the neighborhood of x naught, if we're just looking at how this wave function behaves on, let's call this guy y. Let's call alpha x minus x naught, let's call it y. We want to know how this guy behaves in the neighborhood of x naught. This will be exponential of alpha y square by 2. Okay, there's a minus sign because sigma 3 is minus, and there's an h bar. All good? And I haven't even checked this, but presumably this is the same as the behavior of a ground state harmonic oscillator of frequency alpha. We know it's a Gaussian, we know it's got some frequency. From dimensional analysis, it's the right thing. So the only thing that could be wrong is some factor of 2, and presumably it's correct. Okay, so we see that we are getting a harmonic oscillator ground state in this neighborhood. Similarly, we will also get a harmonic oscillator ground state in this neighborhood. Okay, but now the question is one of coefficients. Okay, now you see what is the difference. We're going to get some coefficient here and some coefficient here for this guy and for this guy. And what is the ratio of these two coefficients? That's a relevant question. Well, there's some stuff involving normalization involving these alphas, because the actual ground state of the harmonic oscillator will have a normalization involving alpha. So I'm ignoring that part. That's a minor thing. The main difference in normalization comes from the fact that while the wave function here is proportional, let's say we did this integral from 0 to, okay, let's say we did this integral from some a to x. The wave function here, okay, apart from this part that we have, has this factor w minus w of x a to x naught. Right, because this thing is being integrated, this is minus, this h bar, I keep forgetting that, 1 by h bar. Okay, so that's the term that, apart from the guy that we've started with, which has given us this. There's also the integral from wherever we started to x naught. And then there's this additional piece, which gave the wave function of the ground state. Whereas, if this was some x naught prime, x naught tilde, this would have the integral e to the power minus 1 by h bar integral a to x naught prime w of x. The ratio between these two coefficients, okay, the ratio between these two coefficients will be this divided by this, but when you take ratio of exponents, it just subtracts. And so what we will get is an e to the power minus x naught prime to x naught. If we take ratio of this divided by this, 1 by h bar w of x dx. X naught tilde was the location of this other guy. Tilde. Right? So if we call this coefficient A and this coefficient B, we will get A by B is equal to e to the power minus 1 by h bar x naught tilde x naught w of x dx. It's a definite integral, notice. All good? Okay?
The coefficients behind this single quadratic solution are only true when you are on that point.
Yeah, we're expanding the wave function in the neighborhood of that point. But an exponential is the integral up to that point, that's all multiplied, times this additional integral. Right, I've just broken up the integral as integral up to x naught plus integral from x naught to x.
That can be done perturbatively.
This one is done perturbatively, that's how we got the y squared.
But so the approximation will not work, right? For this long range.
For what? Oh, the perturbative approximation is only for y. Yes, this part is exact. Okay? So what we've got is that this a by b is e to the power minus 1 by h bar, integral of x tilde to x naught.
Here you use the non-perturbative answer.
I use the non-perturbative. So if I'm just getting the answer, then we will interpret. Right? We're seeing non-perturbatively that this is true. Okay? Notice that this is not 100% true. We have to correct it. The correction is to add the additional normalization factors that come from frequency. 1 upon square root of frequency. But those are extremely minor compared to these. So just to avoid distracting from inessentials, we'll forget those terms. Those would be essentially determinants, but forget all that. Okay, so now the question.
Up to over constant you can get it, right?
We can get it exactly.
Exactly, yes.
But you see, the constant requires normalized wave functions for the ground state oscillator, and that normalization involves frequencies. And these two frequencies are not the same.
2 and 1, yeah.
Okay? Actually, in this problem that I've written, they are the same.
Yes, they are the same.
Because there's an x goes to minus x symmetry. But in general, they're not the same. Okay? So in general, this is not, there's an error involving 1 over square root of frequencies, which is easy to work out. I'm just not working it out because it's not important. Okay? Great. So what we want to do is to figure out why this ratio came about. Okay? Please.
This can be, I think, explained by tunneling, because if the area is positive, it means that the potential bump near the right wala solution is bigger. So that will not tunnel much as compared to the left one.
Exactly right. Exactly right.
Solution will take care.
Exactly right. So as Shoaib says, this is coming really from either WKB approximation or from an instant turn. These are the same things. It's tunneling, as he says. Okay? And we're going to try to get this feature out as accurately as we can. Okay? So how are we going to think about this problem? You see, we understood from our semi-classical point of view that the problem has, the low energy behavior of this problem has 3 low energy states, 3 states which had 0 energy in perturbation theory. Okay? Now what we're going to do is some tunneling, some WKB, non-perturbative mixing between these states. Clearly other states are out of the game. The whole problem is within these three states. Oh, by the way, before we start anything, we could ask, why is it a linear combination just of those 2 states? Why not the guy in the middle? In this problem, it's very obvious why. It's very obvious why, because the Hamiltonian of our problem had a sigma 3 in it, which commuted with spin. So in this problem, we can simultaneously diagonalize both energy as well as spin. So the spin, if there's a single state, it will have a definite spin quantum number. It will not mix with the other spin. Okay? So it's clear why it's happening. And we will come back to that. Okay. So if we wanted an effective Hamiltonian, it's just some effective 2 cross 2 Hamiltonian. Just in this up spin sector, whereas the down spin sectors. Okay? However, since we're studying supersymmetry and since this problem is a nice problem, it's nicer to work out not the effective Hamiltonian on the space of 3 states, but the effective supersymmetry operator. Okay? Now, let us remember that the supersymmetry operator does not commute with spin. In fact, the supersymmetry operator Q was sort of went like sigma plus, and Q bar went like sigma minus. Okay? So let's give these states names. These perturbative states, let's call this guy 1, let's call this guy 2, and let's call this guy 3. Okay? And what I'm going to try to do is to work out I, Q, J, where I and J equals 1 to 3. And similarly for Q bar. Now once we worked out Q, we know what Q bar is because Q bar is the Hermitian conjugate of Q. So as a 3 cross 3 matrix, it will be just the Hermitian conjugate. Is this clear? Now you might ask, why am I working out Q? I'm interested in the Hamiltonian. Well, we know how to get the Hamiltonian from Q, right? Q bar plus Q bar Q is twice the Hamiltonian. So once we've worked out Q, we know the Hamiltonian. Since we're working on a problem with supersymmetry, it's nicer to work out the supersymmetry operator than to work out the Hamiltonian directly and get the Hamiltonian as a consequence. Because as you guys know, roughly speaking, the supersymmetry is square root of the Hamiltonian. So it's nicer to work with the more primitive object than its square. But the supersymmetry operator has the disadvantage that it does not act only in this 2-dimensional space. It acts on the full 3-dimensional space because it flip spins. But it acts very simply. Okay, so the question that we want to ask, as we've discussed, is how the supersymmetry operator acts. Okay, now this action of the supersymmetry operator can be split into action in spin space and action in X space. The operator factorizes into product sigma plus times some X business. Okay, so let's first look at the action in spin space. There it's totally trivial, right? Because the action in spin space is just Q behaves like sigma plus. Now, so we get 3Q, let's call them A and B. Let's call 1 and 2 A and B. All other matrix elements are 0. Okay? In spin space, that's how it acts. Fine. Now that we've taken account of spin space, what is left is just plain old quantum mechanics with no 2 components. Just nice 1-component quantum mechanics. Okay? And now what we want is the amplitude for A, which was 1 or 2. So this guy or this guy, the amplitude for these 2 states to go to 3, which was the guy in the middle. Now remember what the potential in our problem was. Our potential was W squared. But all of you know how to work out such an amplitude using WKB approximation. Okay, WKB approximation. We will do it a little more sophisticatedly by the end of this class using an instant term in a more complicated context. W prime sigma. W prime sigma was also there, that's correct. Okay. Okay, W prime sigma. How does that? But that came with an H bar. Right? So that's going to be at the same order as the determinant around this W. Okay? Let's do it in leading order in H, up there. Okay? So we should, do WKB also in a whole power series expansion in H bar. Right? I'm just going to do first leading order. Okay? The potential, classical potential, was W squared. Okay? There was W squared perhaps by 2. No, W squared by 2. Okay? And what we want in WKB is to compute the effective momentum and take integral over distance. Right? So the effective momentum is p squared by 2, our mass was 1. So p squared by 2 plus W squared by 2 is equal to the energy conservation. Okay? But we're looking for 0 energy states. So energy is 0. So we have P is equal to minus W square. P squared is equal to minus W square. The minus tells us instead of i's, we will have plus minus. We're looking for the amplitude will be some decay. As it works, as you know, in WKB, the mixing will be the decay. So what we will want is that this mixing amplitude from there to there, let's say we want from 1 to 3, will be an integral like x naught tilde to x mid mod W of x dx e to the power minus of this. Okay, so this will be, so we've concluded that we can be more completely exact, keeping track of determinants around this and so on. But yeah.
Why am I getting mod?
Why am I getting mod? Because you see the potential was W square. And what we want is square root of potential. So we take mod when we take the square root. Right? We don't want to get some blow up ever, right? There's a potential suppression. You're tunneling through a potential. Is this clear? Okay. And so what we've concluded so far is that the amplitude to go from 3, we call that 1. So Q1 is equal to e to the power minus x naught tilde x mod W of x mod W of x dx. Okay? With our particular potential, actually, W between x naught tilde and x mid was positive. So for this term, I could have dropped the mod, but I wouldn't be able to drop it for the other term, so I'll just keep it. Okay. And then we also, in a similar way, get that 3q to 2 will be equal to e to the power minus, and now we want, always a positive answer. So x mid to x naught mod W of x dx, and all other amplitudes are 0. Is this okay? Okay. So what? Now let's call this quantity, just because it's a cumbersome quantity, I'm going to call it alpha, and this quantity I'll call beta, and we will come back, substitute them back when we need. So what does the Q operator look like? Okay. So what does the Q operator look like? So suppose this is row and this is column. Okay. Then first row, third column is an alpha. Second row, third column is a beta, and everything else is 0. What?
1, 2, 3. 1, 2, 3. I mean, it's 1, 2, 3.
1q3.
The complex, yeah. 3q1 you calculated.
Oh, Q1, 1q3 is 0. Because Q is sigma plus. Okay, but Q bar, you just take complex conjugate of that. You'll get the amplitudes of its Hermitian conjugate. So we'll just compute the matrix for Q and then take its Hermitian conjugate for Q bar. Right? Remember, Q is not a Hermitian operator. Okay, Q1 and Q2 were Hermitian operators, but we soon graduated to looking at their complex linear combinations which were not Hermitian. It's much more convenient. Okay, all good? Shuman's looking unhappy.
So what this is that it can go one state can
Q can take 1 to 3,
Q can take 1.
or Q can take 2 to 3, but Q can't take 3 to 1.
It's the raising operator.
Yes, it's Q. Okay. In the same way, Q bar will be its Hermitian conjugate, but all these numbers were real. We don't have to worry about complex conjugation. We just have to take transpose. Okay, and so we get 0, 0, 0, 0, 0, 0, alpha, beta, 0. And now we can compute Q bar plus Q bar Q. Twice, that's twice the Hamiltonian. Okay? You know, irrespective of the details of these numbers, this shows you, this is a general feature that we'll use again and again when we study supersymmetry. That is, when you've got something, you've isolated through some approximate calculation that there are few low energy states. Then you do something non-perturbative. The non-perturbative stuff will only happen on those few low energy states. And so it's very simple. In this case, it's just a 3×3 matrix. You know, this attitude becomes, is often used and becomes even more useful when we study quantum field theory, often, as we will see as we go. Okay? So, great. So now let's compute Q bar. So Q bar is equal to, let's see. So Q bar, I get alpha squared, help me if I'm doing it wrong, alpha beta 0, then beta alpha, beta squared 0, 0, 0, 0. Is this okay? What about Q bar Q? Okay. Q bar Q has only third row non-zero. And third row is alpha squared, beta squared 0. Okay? Therefore, when we add up Q bar, so 2H, okay, 2H is the sum of these two. That's alpha squared, alpha beta 0, beta alpha, so alpha beta 0, sorry, alpha beta, beta squared 0, alpha squared, beta squared 0.
0, 0, alpha square plus beta square, right?
The bottom right term should be alpha square.
Only third, the bottom element is
The bottom left term should be alpha square plus beta square.
Alpha squared, I did it wrong, let me check that. Q bar, and there is Q, you're right. This is,
both are 0. Diagonal element is the alpha square.
thank you. You're saying that only the third 3, 3. Thank you. Okay, very good, thank you. We would have got nonsense if you hadn't helped. Okay. Now what is this telling you? What is this telling you? This is block diagonal. This is a 1×1 block. It's got a non-zero eigenvalue alpha squared plus beta squared. So there's no hope for that guy. He's gone. Okay? This cannot be the zero energy eigenstate. But good, because 3 was the middle guy. 3 had the wrong spin. 3 was spin up. We knew the right eigenvalue will be spin down. Had to be some mixture of 1 and 2. Okay, had I done my nonsense, you hadn't helped me, we would have run into trouble, probably. But okay, so we've got, so this guy is lifted, its energy is lifted, and we know the magnitude of its energy lifting. It's alpha squared plus beta squared, where alpha squared and beta squared were what we computed. Okay? But what about here? Here is there still a zero eigenvalue? Well, it's a question of whether this 2×2 determinant is 0 or not. But it is, because alpha squared beta squared minus alpha squared beta squared is 0. Okay, so there's a 0 eigenvalue there. Okay? The non-zero eigenvalue will be of the same order alpha squared, beta squared, maybe an alpha beta. But the 0 eigenvalue is special and it continues to exist. Okay? So the 0 eigenvalue, well, what is it? We just have to solve this on psi is equal to 0. And let's see if I put a beta here and a minus alpha here, I should do it. Right? Right? So my 0 eigenvalue is this linear combination beta alpha in modulus, some minus sign. Okay? In modulus it's beta alpha. Let's get the ratio of these two. Okay, so the ratio of these two, now what had we, let's see if we can look up there. We had got A by B, where A was the what we called 2 and B is what we called 1. So A by B was, let's write that again. I'll write it here. So A, and we'll remind ourselves that that is 2, B, which we'll remind ourselves is 1, was equal to e to the power minus 1 by h bar x naught tilde to x naught w of x dx. Okay, but A was what we called 2, so so it should be this by this. Okay, so this we should identify with alpha by beta. Let's check if that's working. Is this correct? Well, alpha was e to the power minus x naught tilde by x mid w of x with a mod dx. That was alpha, and now we will take plus, because integral x naught x mid to x naught mod w of x dx. That was because we had to divide by beta. But then we used that here mod made no difference because it was positive. But here mod made a difference. So we can make this minus and take out all mods. And that's equal to e to the power minus x naught tilde to x naught w of x dx. Exactly as we expected. Now if you do this more carefully, you can try to keep track of phases. You can try to keep track of h bar corrections and so on. And since we have the exact answer, everything should be reproduced. Okay, I'm not going to try to do it that carefully. As perhaps you can guess, it's always a question for me whether it will work at the end. My level of preparation is not such that I know it's going to work. But even this working is a major accomplishment for me. So we'll just stop this discussion here. As you will see later in this class, we will come back to a more sophisticated version of it in a more sophisticated context. Any questions or comments about this? Okay. I have one last comment. Suppose we were working with a W that looked like this. According to our rules, this is the down and this is an up. Now, can somebody quickly tell me, use the same reasoning that we used to help me understand that this will be completely lifted? exactly. Exactly. So as Sunil said, Q, let's call this 1 and this 2. So the only non-zero element for Q is 2Q. Q was raising or lowering? Q was raising, yeah. Q21. It's the only non-zero element. So we call this row in this column. Then Q in this case is the has this structure. Row 1, column 2. So this. No, row 1, column 2. This. Okay, 0, 0, 0. Some alpha. Q bar will be its complex conjugate, Hermitian conjugate. I'm assuming it's real, otherwise alpha bar. And now Q bar will be equal to alpha bar 0, 0, 0, and Q bar Q will be equal to 0, 0, 0, alpha bar. Correct this time. Okay. And therefore we have 2H is equal to alpha bar times identity. Every state is lifted. Okay. So you see how computable tunnelings are able to break supersymmetry, lift states. All very simple physics, all simple undergraduate physics that you're all very familiar with, but works out so beautifully in this model where we also have the exact answer. Okay? Excellent. Excellent. Now, let us return to our main discussion. I wanted to complete the discussion of the sigma model. Okay. So, let me write down a few formulas so that you remember the context. And I think it's maybe time for us. We've been using this chi and psi, but the rest of the world, and in particular Witten, uses psi and psi bar. So I think it's time for us to reluctantly switch conventions. So we'll write it down, and I'll also tell you what the change of convention is. Okay, our Lagrangian had an I chi psi dot, and Witten's Lagrangian has a I has an I psi bar psi dot. Unfortunately, Witten puts a half. Anyway, that fine. So no, but that's that. No, it's correct. So our Lagrangian had an I. Yeah, so I think what Witten calls psi bar is our chi, and what we call psi is his psi. Okay, so okay, notation. Chi will sometimes from now on go to psi bar, but psi stays psi. Okay, sometimes if we get lazy, we might write chi again. Chi and psi bar are the same thing. I'm doing this only because everyone else who writes papers on the subject, I mean everyone who writes papers, we're not yet writing papers on the subject. So everyone who writes papers on the subject uses this notation. Okay, so we should just stick to it. It's just a name, okay. Psi bar is just it's another name. I don't like that notation because immediately you start thinking of complex conjugates. And it may or may not be complex conjugate, it doesn't matter at this point. It's just another anti-commuting variable. Okay? But since everyone else does it, we'll do it.
Will it be something like gamma naught psi?
Well, gamma naught, if we are working in, you are working in 1 dimension, 2 dimensions, which dimension? If we get this from a sigma model, Okay, so Shoaib's question is this. Oftentimes, the way this Lagrangian arises in actual physical applications is we're working with a higher dimensional field theory. And then we want to restrict attention to the zero momentum sector. In that case, there is a clear relationship to what we called chi is to some other spinner which has definite meaning in higher dimension. For instance, it's often that you go from 2 dimensions to 1 dimension. And then you get a psi bar like this from some other well-defined notion of psi bar in some higher dimension involving gamma naughts and so on. I think that's what you had in mind. But at the moment, we don't have some higher dimension. So it's not a, that's for the future. For us, it's just some independent variable. Okay, all clear? Good. So, just to briefly remind you, and you must correct me if I'm getting something wrong, our Lagrangian was Gij phi I dot phi j dot by 2. Phi I dot just means ordinary time derivative. Okay? But then there's plus I, what we'd call chi, but now I'm calling psi bar. Psi bar I, and then d by dt, psi I. Okay? Plus the curvature tensor whose coefficient we didn't compute. We left that to you as an exercise. But Witten claims it's 1/4, so let's believe him. Okay, and later when we add a potential, there are more terms, but at the moment this was a Lagrange. Yes.
Sir, you have a manifold in Rn, right? So there is no Minkowski space here, right?
The target space is Rn.
So by writing an d by dt integral, how are we making that incoherent in that sense?
Very good. This we discussed briefly last time, but let me say it again. What does d by dt mean? T is not part of the target space manifold. It's just on our time. So you might think, what do you mean by covariant derivative here? However, remember that position on this manifold is a function of time. Now, this quantity here, psi I, is an element in the tangent space of the manifold. It's a vector. Okay, or lower down will be lower tangent space. Okay, now when you take a derivative, suppose you have, suppose I'm taking a derivative and I'm trying to subtract 2 tangent space vectors. If I try to subtract a tangent space vector here from one here,
I'm going to bring that to the bipolar transport.
yes. Okay, now because we're taking this at different times, and because x,
We are considering that we are on curve.
some curve, exactly, which is a function of time. So when we take this derivative, we're taking what this means is this vector minus this vector.
So we need to bring that.
We need to bring that back. So what does this mean? How much we need to bring it back by? Well, phi I dot dt. Okay? And so when you work that out, as we discussed last time, the formula for this d psi I by dt is equal to psi I dot, I'm putting, this is correct now if I put an upper index, plus gamma I mn phi m dot, phi is our coordinates. It's the coordinates on the manifold.
I was previously x, right?
It was previously x, let's call it x. Capital small x, sorry. Again, phi is what Witten uses, which is why, but that's, no, it's fine, but whatever, it doesn't matter. X, I, j, did I say capital I, capital J?
Small x.
Small x. X, I dot, x, j dot, sorry, Sorry about that. Xi dot, xj dot, we'll call this.
And the sides are also dotted with GIJ. Second term.
This is also dotted with gij. I've written one up, one down, so that's why I didn't. Yeah, but always GIJs. If we write both up, they will always have GIJs.
Third term, the order is different. You had chi, chi, psi, psi.
I had chi, chi, psi, psi, and I, j. What you have to have is these two multiply the same guy. And these two multiply the same guy. Because these two are antisymmetric. And these two are symmetric. So it has to be, and then which ones you multiply with doesn't matter. So there's only one possible order. You may write it in different ways, but it's all the same. Right? What you have to have is that these two are contracted by the same. So he's done that, I, j. And these two are contracted with the same, k, l. Okay? And then you can't complain that I got the sign wrong because I never committed on a number. Okay.
No, but even if you change the psi and psi bar, you have to do it in the both.
Probably twice, yes. His complaint might be that I wrote it as psi bar I, psi bar j, psi k, psi l, which is opposite to this with the minus sign. But we weren't careful about this. We didn't claim to know the answer to this. You guys are going to work out this sign, right? This sign and this number, using the Gaussian normal coordinates and all the stuff we discussed last time. That was your exercise. Wasn't there a term where d by dt acts on psi bar? Well, by integration by parts. These are the same terms.
Oh, you remove the half.
Yes. For the second term, I don't write it with a half. Maybe Witten does.
So you have to complete that term.
Which term? Psi m, and then there is psi n. The usual formula for derivative along this direction. Right? Excellent. So this was our Lagrangian. Now we wanted to understand the canonical formulation of this Lagrangian. I gave you the answer last time, but I want to explain in a little more detail why that's correct. Okay, so you take this Lagrangian and you canonically quantize it, or you equivalently take the path integral obtained from this Lagrangian, you cut it and give it a Hilbert space interpretation. Okay, we know that this Hilbert space interpretation has operators psi bar psi, okay, which will become like sigma plus sigma minus for their corresponding two-state systems. Okay, and we know that they're going to obey commutation relations, which are basically the ones we derived, except there's going to be a metric. Okay, so you will get psi bar I, psi j is equal to gij. Right, if you go to tangent space vectors, dotting psi with Wehrbeins, you can really make them exactly what we had. Right? And these things can be thought of as the translation from the Wehrbein indices to the metric indices. That's why the gij. Do you know what I mean? Right? We could work with dotting with a Wehrbein, and then it's exactly what we had, and then undotting that gives us this. Is this okay? Fine. So this is sort of clear. Sure. What?
Why there is no iota? Usually in QFT we have iota.
Oh, psi bar, because this had an I. Right? The way to understand that is that we got this Lagrangian. You remember how we built it from coherent states? We got this Lagrangian with an I, where psi bar was chi, which was sigma plus, and psi was psi, which was sigma minus. Sigma plus, sigma minus don't have an I. Okay, but it's equivalent to the fact that they came with an I. Okay, excellent, good. So this is clear. But we still want the canonical formulation for x. Of course, it's straightforward, but not entirely straightforward. Why not? Because when we compute pi, that's derivative of the Lagrangian with respect to xi dot, sure we get xi dot, where that's xi dot lowered with g. You understand, right? Sure we get that. But we also get a term from here. Okay. And the additional term we get is plus I psi bar. Okay, so now this I should be this I. So let's call this J. This is now gamma I, because that was this. This is N psi N. Where's the J? That is the gamma has 3 indices. So where did I mess up? Sorry. This I was going to be that. Sorry.
You can lower the J on psi bar. The J on gamma.
Yes. Sorry. Give me a minute. Suppose I wrote this originally as JJ. Let me write JJ and J here. That's what you were suggesting. Yes. Thank you. Okay. Thank you. Okay, so now suppose I do that, then this has, here I was acting with I, so this was a J, so this thing comes here with a J, up J, then this one came with a lower J, and now it looks good. Thank you. Okay. Okay, so we have pi is this. Okay, now if we write xi dot, what is that in terms of pi? So that is equal to pi minus I psi bar j gamma I n j psi n. Now we know in canonical formulation, we know that pi is just del by del xi. But that's ordinary derivative. It's just del by del xi. So suppose we have pi acting on a form. You remember, right, from last lecture, how we're going to build up forms?
It is del by del xi only in the, when we are building a flat space.
No, it's just del by del xi because it's canonically conjugate to xi. Whatever is canonically conjugate to xi will be implemented as del by del xi. Okay? So pi will always be del by del xi. Where del by del xi is not some fancy del, it's just derivative. Okay? But look at this now. You remember we're going to build up forms. Where forms were built by creation operators, chis or psi bars. Acting on the spin vacuum. If you want a P form, you act with P psi bars on the spin vacuum. Now, what does this guy do? What this guy does, suppose we had, let's say to start with a 1 form. Okay, so we had a psi bar M. This guy will annihilate this and replace it by this. So suppose we had a vector field like this, AM psi bar M. Okay, how will this act? This part will kill this, okay, so this m will come here. So we'll get gamma I m a m j psi bar j. And you see this is exactly what is needed to turn the derivative into the covariant derivative. To show you it's exactly what is needed, I have to show you the signs are also working. Okay, I hope I've done the signs correct. Let's see. P is what? I del by del x? Minus I. So, so this is minus I del by del x. Minus I, let's take up then a minus I overall outside. Minus, oh, it's working. Wonderful. Del by del x I plus gamma I m j am with sides. It's giving you the covariant derivative and vector. Amazing.
So where is AM came from?
AM, because you see, the state in our Hilbert space was forms, which has some index and then a coefficient function, which is a function of x. That was AM of x. Okay, if you would had preferred, I could have had this up, this down. We would have got some minus sign from the fact that you'd have to take this through. Okay, and you would have got the minus sign for acting on a lower index object. So, while Pi is the operator del by del xi, xi dot is the operator minus I del by del xi, xi dot is the operator minus I times d by dt, d by di. Right? It's a covariant derivative. Okay? So we've got the rule for canonical quantization. The rule is telling us that Pi goes to del I, but x minus I. As you've noticed, I've dropped all h bars at some point. Okay, xi dot goes to minus I del I. Okay, something very similar happens when you study electromagnetism. When you study electromagnetism, I mean a charged particle moving in an electromagnetic field, you find that the canonical momentum proportional to I, okay, the canonical, which is del by del xi, includes xi dot minus ai. Okay, but xi dot itself then turns into the covariant derivative. This is good because xi dot is a physical thing. Okay, so it should map to a physical operator. That's roughly the idea. Whereas Pi is some abstract, in some mathematician's head. What it does, it does. Right, but xi dot is how fast a particle is moving. Now, it's a very physical thing. Okay, excellent. So this is the rule we've got for canonical quantization.
Instead of minus I del xi, if you take Pi to be anything else, you will in the end you will get the same xi dot.
What do you mean to be anything else? It has to be this, because it has to be the canonical commutation relation.
No, I mean you said it is.
Oh, no, I said it's not physical because it seems to be coordinate dependent. This is a coordinate independent thing. It's a geometrical thing. Okay, it doesn't matter which choice of coordinate you've used. The canonical formulation is not coordinate independent because you're finding the canonical conjugate to a particular coordinate. So its momentum is not a particularly nice thing. Okay? Excellent. So, good. So far, so we've got this, so we've got now the rules of a canonical formulation very clear. Right? So, our rules are this plus the fact that those guys are the versions of sigma plus and sigma minus that are scaled to obey Gij. Nikhil, you had asked me what I meant by this Wehrbein thing. Is that still confusing? Shall I tell you? It's just this. I don't know how familiar you guys are with it, but if you're not familiar, it's a good time to learn. You see, whenever you do general relativity, you're studying a manifold. I'm going to say it in the context of Euclidean manifold, but exactly the same idea works for general relativity. It's a good idea, it's sometimes a good idea, to erect a set of orthogonal vectors at each point in space. Okay? Suppose we are looking at some d-dimensional manifold. We erect a set of orthogonal vectors whose they're vector fields, but they're labeled by m. Okay? So that m mu is equal to 1 to d, and m also runs from 1 to d. Mu and m have completely different logical status. M is a which vector index? You're putting a bunch of vectors that are orthogonal to each other in that space. Mu are the components in the coordinate system that you are working. Okay? These m should be thought of as geometrical vector fields. EMs are vector fields, so they are coordinate independent. Specification of arrows all over the manifold. But their components in your particular coordinate set system are EM. Okay. Now, the fact that these things are orthogonal to each other tell you that G mu nu EM mu En nu is equal to delta Mn. Okay? And then by doing various manipulations with matrices, then you define E at some point x. So this whole thing is as a function of x.
Yeah, it will change from each one.
Each point. And since I've not introduced any derivatives at the moment, point by point you can do it. Okay. Now, you can define the guy with up m and down nu as the inverse of the matrix. This is an d cross d matrix at any point. So it has a matrix inverse which we define to be this object. Okay? And then you can convince yourself, this is basically that statement. But anyway, you can convince yourself of various identities. So Em mu En m nu sum over m is equal to G mu nu. Similarly, a similar relationship for this guy and so on. So this is just decomposition of the space into these orthogonal things. Now, oftentimes it's useful to think of things that live in the tangent space as having Mn indices. The Mn indices behave exactly like they would in flat space, at least as far as normalization is concerned, because Emn are unit normalized. Okay? So, in this Mn space, we could literally erect sigma plus and sigma minus matrices, one for each Mn direction. Okay? So, there's literally a sigma plus m and a sigma minus m. Okay? So, sigma plus m and sigma minus m obey the relations sigma plus m sigma minus n is equal to delta mn sigma plus m with sigma plus n is 0 and so on. And now you define those sigma mu matrices. Sigma mu matrices, the thing that will be psi mu. You define sigma, what did I call it? Psi mu. This was psi bar mu, same as sigma plus mu, to be equal to mu sigma plus m. Okay, this is now the definition of what the psi mu is. So if you worked with these Mn, you just had our old formalism with the old normalization, and then you convert with these E's. It's often a convenient trick. It's essentially Einstein's equivalence principle. Well, part of Einstein's equivalence principle, that every region of space can be thought of as flat space. Here we use it in a very trivial way, not even in the sense of derivatives, just at that point. But for that point, you can treat it as being flat space. That's what the Mn indices are doing. Okay, so fine, let's continue. What? At each point. Actually, we're not even changing coordinate. We're just referring. Suppose I give you a vector field A mu. I can now find its components in each of the mn directions at each point, just by dotting with the mn mu. So not even changing coordinates. We're just giving the information of that vector field by specifying its coordinate, its projections onto this Wehrbein separately at each point, as you say.
We are just changing the coordinates at each point. That's the same thing, I guess.
It's the same thing, except that there may not, in the tangent space, there may not be a global coordinate which has these components. Okay? So these anyway, yeah, fine, we could just keep discussing, right? Right, but it's very similar to changing coordinates at each point, but it's not exactly the same. It's projecting onto this pre-assigned basis. Okay, excellent. So now, why did I say all this? I said all this because we wanted to find the supersymmetry operators in the canonical formalism. Okay. Now, in order to know that, how am I going to do this? I'm going to use the fact that from our superfield language, we know how components x, psi, chi transform under supersymmetry. Okay? We know how that happens, and then using that, I'm going to figure out what the supersymmetry generator was. The thing whose commutator, anti-commutator with the right field will give you the right transformations. Okay? Is the goal clear? Okay. So, let's start with the simplest guy. This is a screenshot from one of the previous lectures which Schumann kindly gave me. We have delta x is equal to I chi. Once we put these I indices, we have delta x I is equal to I chi. Now I should call this psi by, right? Delta, this is delta under q. Okay, now given this, what would your guess for the supersymmetry generator? For a supersymmetry generator. What? X dot psi. Very good. Except not quite x dot. Should be p up to i's and so on. I'm not keeping track of. Do that properly. So. Because the commutator of this with xi, it's pi that has canonical commutators with xi. Okay? To some i's and signs and so on. So clearly this is the kind of thing that we want. Okay, but there could also be some additional stuff that does not that has non-zero commutator with xi. So maybe in the end Diksha was correct. Okay, so really what we know is that it's pi psi by plus something independent of pi, because pi is the only object that has non-zero commutator with xi. Okay, so with some function of xi psi I psi by. Yeah. Okay, excellent. Now, to nail down these functions, we have to look at the other commutators. Okay, so let me remind you of the other commutators. We had del theta of psi bar is equal to 0. This tells us that our function, whatever it is, should have no size. This had no size, so that's good. But this should not be good, because otherwise you won't get 0. Okay? And the next thing we had was that del theta of psi I was equal to dxi dot by dt. Sorry, what? Oh, f is 0 in our game. Oh, sorry, no, there's no x. Oh yeah, what am I saying? It's just xi dot, xi dot. Sorry, what? No, not for xi dot, because xi dot by itself is a vector field. Had we had a psi I dot, that would have become a covariant derivative. But xi dot is not, just like in the Lagrangian, xi dot was xi dot. It's just xi dot. Is this clear? It's not like xi dot was the derivative of a more primitive geometrical object. Xi dot by itself is the least primitive geometrical object, namely a vector field. Coordinate is not a geometrical object. Okay? Good. So now we can figure out what we got here, because the commutator of psi bar with psi should give us xi dot. So even though I told Diksha she wasn't correct, she was. You see, because the difference between xi dot and pi was some stuff that was not involving xi. Okay? So it could be added without you being able to see that. Okay? So in the end, our generator, and we have to get all the i's and minuses correct, I'll leave that to you, is xi dot, where are we? Xi dot and psi I. Psi by. This was our generator. But in the canonical formulation, xi dot became covariant derivative. Okay? So the final result is that q is equal to psi bar I di. Psi bar you can replace by gamma matrices, correct? Absolutely, absolutely, absolutely. So it's psi bar acting on forms. And q bar is equal to psi I di. Similar consideration.
Gamma matrices means the equivalent of that sigma plus and sigma minus.
Gamma matrices, she's saying from a very sophisticated point of view. From our point of view, psi bar is just something that adds an index to a form, and psi is something that removes an index to a form. But since we have someone sophisticated with us, let me give you 2 minutes on why she said gamma matrices. You know, there is a very deep connection between forms and spinors. And the connection has a very simple group theoretic origin. The group theoretic origin of this connection is the fact that the tensor product of spinor with itself, the square of a spinor, is the set of all forms. This, you know, so if you take the Clebsch-Gordon decomposition of a spinor with another spinor, the decomposition is all forms. This, in some language, all of you know. It is merely the statement that when we are studying the Dirac equation, you've got a psi bar and a psi, you can put either identity here, and you get a Lorentz invariant, which is a scalar. Or you could put gamma mu here, and you get a Lorentz invariant, which is a vector. Or you could put gamma mu, gamma nu here, and you get a Lorentz invariant, which is 2 tensor. And you can keep going, but you can't go more than the dimension of space. So you get, so the decomposition, the content of spinors is, of 2 spinors, is in the set of all antisymmetric tensors. Group theoretically, this is the state. It's, it's like the statement that you're familiar with, like a statement that vector times vector, scalar plus vector plus tensor. It's that kind of statement. Spinor times spinor is antisymmetric 0 form plus antisymmetric 1 form plus an antisymmetric 2 form and so on. Now, to make the statement exactly correctly, I should tell you about whether I'm looking at chiral spinors or not, so on. But let's not be so precise. Okay, so whenever you have the set of all forms, on the set of all forms, you're actually looking at the set of all bispinors. So if you've got an operator that acts on forms, it's also an operator that acts on bispinors. Okay? Now, in this space, psi bar plus psi bar I plus psi I, okay, obeys all the properties, maybe by 2, obeys all the properties of a gamma matrix. Okay, with different guys they anti-commute, but with the same guys they square to 1 because psi bar with psi is 1. Maybe I need some factor of square root 2. Okay, it squares to identity with some number. In fact, it comes right. So it's just right because you do gamma I gamma j, anti-commutator is equal to gij, anti-commutator. So then I put a by 2 and then I'm happy. I think this will now, or square root 2, sorry, with some factor, this has all the properties of gamma matrices. However, there's another construction, it's also Hermitian by the way. There's another construction that also has all the properties of gamma matrices. Because psi bar is the Hermitian conjugate of psi. Because one creates, the other destroys, sigma plus sigma minus.
They are not independent.
As operators on spin space, they're Hermitian conjugates. Sigma plus and sigma minus are Hermitian conjugates.
Yeah, that
It's just that statement. These are operators just, what?
At the starting, you started with
Completely independent.
okay.
Completely independent. But one was representing sigma plus and the other was representing sigma minus. And so, when they become operators on this spin space, they are Hermitian operators. Not as fields. They're completely as anti-commuting fields. They're entirely just independent fields. But the operators that they become after canonical quantization are Hermitian conjugate. This is a property just of the anti-commuting path integral. If you have I chi dot psi, chi and psi will turn into Hermitian conjugate operators, as we saw, right, from our derivation. Okay, excellent. So now on this, all these operators of course act on this full form space, but actually since there's no x in it, they're acting just at pointwise. So they're just acting in some 2 to the power d dimension, 2 to the power d dimensional space, the space of all forms. Why is the space of all forms 2 to the power d dimension?
Some of the wedge part spaces.
Some of the wedge. Each index is either there or not.
NC1, NC2.
Exactly. Exactly. Okay, so in this 2 to the power d dimensional space, these guys each obey the gamma matrix algebra and also anti-commute with each other. Can you see that they anti-commute with each other? It's because this has a plus and that has a minus. That will cancel. It's very similar to the D with Q. It's very similar algebra to D with Q. Okay? Now, if you put, for instance, let's say we're in even dimension, and I add a chirality operator. So I call this gamma I. I call this gamma tilde I. And I define some new gamma tilde I prime, which is equal to gamma tilde I times gamma chirality, product of all of these. Then these two commute with each other. Because originally they anti-commuted, but because every gamma I commutes with gamma chirality, Now the new sets of two sets of gamma matrices commute with each other. If this is not making sense, please forgive, ignore it. This is just to answer to address Diksha's question. Okay, so now we've got two sets of commuting gamma matrices. Clearly, they must be the gamma matrices that act on the two different spinors, because forms are bispinors. Okay, and this is the sense in which, at least I think Diksha was saying, these are just gamma matrices. Thinking of forms as spinors, psi plus psi bar and psi minus psi bar act as gamma matrices on each of the different spinor indices independently. And there's actually lots you can do here with this idea. This business about Betti numbers and the cohomology can be worded in this language. The Euler character is an index of the operator D, but all that will come to later. Okay, let's move on. Okay, and this was just to since Diksha brought it up, just to mention it. Okay, so now we're in business. We know what our supersymmetry operators are. Okay. So our supersymmetry operators were psi I di and psi bar I di. Probably. Yes, there should be. Minus iota. Let me look that up just a minute. Let's see. Well, yes, there should be. Of course, yes. Though we haven't been so careful. I'm a bit worried about agreeing to that because we had I there and so on. I'll request you to check that carefully. Okay, I'll in fact quote what Witten says as operators. Yeah, but he has eyes. Yeah. Oh, no. Yeah, right. Oh, no eyes. But he has one of them minus. I don't really know why. I minus I. He puts this and this. I'm not entirely sure why. Okay, I hope he's not using some different conventions and so on. Okay, forgive the pluses and minuses and i's here. We can do that carefully. Yes, please go on.
This size can be written as you said, E m mu times sigma n.
Yes.
Written in this I indices is like using the m indices.
Yeah.
Oh, sorry, no.
This I at the moment is space-time index. I should write it as mu. But if you wrote it in the m indices, it would be the same thing. Because when you contract m indices, it's the same as contracting space-time indices. So you can think of it that way if you wanted.
I mean, E will go away.
E goes away. So either way, it's the same thing. But think of it as space-time. Okay. Okay. Now that we've got these two things, now we can interpret what the Q's and Q bars are. You see, what is this operator? This operator adds, you remember our Hilbert space was psi bar I1, psi bar I2, psi bar I3 times AI1, I2, I3 of X, this kind of states. Okay? This operator here adds one more psi bar, but acts with a derivative. So what does it do? It adds a covariant derivative here and acts one more psi bar. The psi bars are completely antisymmetric, so it antisymmetrizes. So this is the D operator, right? Because it adds an index, adds a derivative, and completely antisymmetrizes. Clear? Okay? This is the D operator, and even the normalization is the one we had before. Because if you write it as many terms, you want to divide by 1 by p plus 1, but we're not writing as many terms. We just get one term, but then it has to be completely antisymmetrized. So the normalization is that of one term, but that's the reason we had the 1 over p plus 1 when we defined that D operator. Is this clear? Okay, so this operator here is the D operator. Maybe if I'd written it with a minus, it would be a minus D operator. Okay, and this operator, what does it do? Well, it kills an index. And whichever index it kills, it replaces with a derivative. That is the D bar operator. Okay? But this operator has a choice of p indices for which to kill. Okay? So that's why it matches the p we used in our definition of the D bar operator for the normalization. Okay? So the supersymmetry operator and its Hermitian conjugate, psi and psi bar, yeah, okay, yeah, these had better be, if one is plus, this had better be minus from hermiticity. Because I del is a Hermitian operator, but del is an anti-Hermitian operator. Okay, so it had better be that if one was plus, the other one was minus. Okay. Equivalently, we could get the same sort of algebra by putting two i's. Maybe like Shoaib wanted, then you won't have the plus and minus. Okay, so these are various conventions, I suppose. And I hope Witten is using the same convention we were using. Okay, but I encourage you to just work this out really carefully with signs, using the conventions we had, and get all the numbers. Okay, so great. So now we're in business. This was our so the supersymmetry was, let's say, D and minus D star, or D star and minus D, doesn't matter very much. Okay, what will the Hamiltonian be? Well, D star plus D star D with a minus sign. Remember, minus del square is the positive operator. This will be 2h. So the Hamiltonian will be minus the Laplacian with some factor of 2. Is this clear? So you see that in this model, supersymmetry is the D operator, supersymmetry bar is the D bar operator, and the Hamiltonian is the Laplacian. Is this clear? Okay, excellent. So this cleaned up, so it took more time than I thought it would, but it cleaned up I claimed this at the end of the last class, but we've explained it. Okay, I now, in the last half an hour of this class, want to use this to learn something new and interesting, unfortunately so far only about mathematics. The first few lectures of this course will be largely about, we'll learn more mathematics than physics. The physics models we study will be very pretty and very nice, very natural, but they aren't the kind that give you a Nobel Prize. Okay, but some of these things may be the kind that gives you the mathematics analog of Nobel Prize. I mean, the Chern-Simons thing did, right? So, okay, the Fields Medal, right? So, these lower dimensional things tend to give cool mathematics. When you go to higher dimensions, you get cooler physics, as we will see. Okay, fine. So now what we're going to do is to take the same model and add a potential function. Yes. Yes. What is that term doing? Well, first it was needed for supersymmetry, but you see, it was an interaction term, correct, involving 4 psi's, right? So what it's doing is acting on forms, p forms, giving you p forms. Yeah, but of course we should be careful, because what it was there in the Lagrangian, but what canonical operator is it affecting? It's not affecting directly the Hamiltonian. Hamiltonian is just del square. So sorry, I don't have anything clever, particular to say about it. It was needed in the Lagrangian in order for this to be for this model to be supersymmetric, and in order for this to be the Hamiltonian. Now you could ask, suppose I just compute the Hamiltonian from canonical quantization. What there is the role of that Rij? It should come about. Okay, let's try that. I don't know, but let's see. Okay, so let's see. So the structure of our theory was Gij xi dot xj dot by 2 plus psi bar I d by dt psi j psi I plus Rij kl psi bar I psi bar j psi k psi l. I'm not writing the numbers, just to get the structures. Okay, this was our model. Now in this model, what we will get here, if we do the canonical quantization, is we're supposed to do the usual thing. Okay, so first split this up. So one term will be I psi I bar psi I dot, and then the other term is plus psi I bar I psi I bar psi gamma. Thank you. Gamma I m n x m dot psi n. Okay. Now this part will have its first order and time, so will carry no Hamiltonian. This part, of course, by itself is first order and time, so it carries no Hamiltonian. So okay, fine, but it affects the canonical. It affects the canonical structure. So here what we have is that the Hamiltonian then will come entirely from this term, but we know that from the canonical structure this is d I dj right, and now the difference between this and the true Hamiltonian, but of course now you also get Hamiltonians from here. So the full Hamiltonian is this plus this. Okay, so this is presumably then an expansion of del square. You see, we wrote our del square as d star d plus d star and d. But you could ask, why do I have to write del square in such a fancy way? Can't I just write it as contraction of covariant derivative? Right? So you might have thought, okay, one natural definition of del square on forms would be d mu, d mu. That's sort of what we're getting from here. That's what we're getting from here. But that's not the same as d star d plus star dd. Okay? And the difference will be carried in this term. Right? It will act on forms by destroying and creating. You understand? Also, this is the prediction that you'll first. Yeah. Anyway, so that's the role of this R, to make the Hamiltonian del square acting on forms as defined by this formula. Notice that when acting on a scalar, it would have no impact because the R term would kill scalars, because it only acts on terms which already have two psi bars, so the psi's could kill it. Okay, so its difference starts from two forms onwards. Okay, so just it's a conversion between del square as we defined it and this other way of thinking of it. Okay, excellent. Now, had we made a Lagrangian which had this del square, it would not have been the square of a supersymmetry operator. You know, the way that a Hamiltonian was the square of supersymmetry operator was that it was d star plus d star d. Without that Rij, it wouldn't have been supersymmetric for that reason. Excellent, excellent question, Sunil. Okay. Let's continue. Okay, so our goal now is to add a potential to our model. We're on the same model moving in a on an arbitrary manifold, but now we want to add a potential function to this model. Okay? So the question we're going to ask is, how does this affect the supersymmetry operators of our theory? Okay? Once again, clearly, our Hilbert space will be the space of forms. Okay? But the supersymmetry operator won't act just like d and d star. It will act in a way that is affected by this potential. Okay, how does it act? That's the question. Okay, so in order to see that, okay, let us note this supersymmetry transformation rule that we had. Now, when we were writing down the supersymmetry transformations, Shoaib objected. He said, you forgot the f term. But we forgot the f term because the f was 0 in the absence of this potential function. But now the f is back, so we have to take it into account. Okay, so let's take into account. Let me remind you that in an earlier class we found that fi was equal to minus I del I by del xi. Derivative of the superpotential. Fi was this object, and we also found that our supersymmetry transformation rules were del theta of psi I is equal to fi plus xi dot. Now, let us remember that this was the key supersymmetry transformation, the one that helped us nail down the supersymmetry transformation properties. Okay. In the absence of this fi dot, we had that psi I was, Q was psi I bar xi dot. Right, that's what we had 5-10 minutes ago. But now we also have this fi. Fi is a function of xi's. Okay, so we should add to it plus fi. But fi was minus I. So this is I xi dot minus I del I by del xi. Okay. Now for this part, now by the way, we're following this paper called Supersymmetry and Morse Theory by Witten. Okay. So the rest of this lecture and maybe the beginning of the next lecture will be following this paper. Okay. Now in this paper, irritatingly enough, Witten changes notation. I becomes little h. So we're going to follow him and change notation. Maybe minus little h, I'm not sure. We'll follow. We get the formulas and then change it. No. I was the superpotential.
Oh,
Capital I. Okay. But he may have made it minus little h. So let's follow for a while. Then let's see. Okay. Now remember that xi was minus I covariant derivative. So we had del psi bar I minus I di. Right. So we'll take minus I out. Di plus del by del x. Xi of I. Okay, clear? Now, Witten has noticed the following. This is, this guy is D. But this guy is what? This guy is adding an index, but instead of adding it with a derivative, adding it with del I by del xi. So do you see that this is exactly the same thing as taking d of e to the power I, acting on whatever, times e to the power minus I. Because the derivative could either act on the form, in which case it's derivative, or it could act on the e to the power I, in which case it would give you this. And then this would come out and kill the e to the power minus I. Okay? So now the supersymmetry operator is not D anymore, but it's very lightly modified. The light modification is that it's acting like this. So now I will check whether Witten has plus h or minus h and switch disk conventions. Plus h. So following Witten, we will relabel I equals h. Okay, and in fact he puts I is equal to t times h. T is just a real number which he will later take to infinity. Okay, and therefore he defines the operator dt, which is e to the power minus th d of whatever times e to the power th on whatever. Okay, and similar modification with the q bar. So q bar becomes the adjoint of this operator because it was
T is
one parameter. We didn't need it, but it will be useful for us. It will be useful for us. D1 is what we had, and of course we could always absorb it into the definition of h, right?
Yeah.
So it's just there for fun, but it'll be useful fun, because we'll get some interesting things by taking t to infinity. Same as taking h to be large, just notationally convenient. Yes?
It seems that this new dt is a similarity transform of the original d. So is it true that this will not change in this superpotential?
Something will not change, something will. As you say, it's a similarity transform, therefore cohomologies will not change. So spectrum of zero energy states will not change. But the Laplacian you form out of d and dt will depend on t. And of course, physics should change, right? We're turning on a potential. Earlier we had a particle freely propagating on a manifold. Now we're turning on a potential. That potential could be very large. So in general, physics will be radically different. But you hit the key point. There is an aspect of the physics that will not change. Okay? D star, dt star is q star. It's just a Hermitian conjugate of this guy. Okay? Hermitian conjugate in the usual way, right? We know the inner product acting in the space of forms. Okay. Now, it is almost obvious that the cohomology of d and d star, or let's say d cohomology. You remember we had three ways of thinking of the same object. One way is all forms that are annihilated by d, but modulo those that are d of something else. The second way is all forms are annihilated by both d and d star. You remember we got that by taking the extremizing in the space of all forms, minimizing the norm. And the third way were forms that were harmonic. All these three were the same. Let me take the point of view that I will look at the first, the most abstract of the three, the cohomology. That is the set of all forms that are declosed modulo those that are d-exact. Now, suppose I've got an element in d cohomology. Okay? I'm now going to produce from that an element in d star in dt cohomology. Okay? So suppose chi was an element in d cohomology. Okay, so what does that mean? It means that d chi was equal to 0, but chi was not equal to d of, let's say, alpha. Okay? I want to argue that if you give me an element in chi cohomology, I will produce for you an element in d cohomology. I will produce for you an element in d t cohomology. Okay, what should that element be? Well, it's very clear. We want something such that dt of that object is 0, but dt differs by multiplying by e to the power minus th. So let's just take chi, chi and define chi t is equal to e to the power minus th, chi. D of that will be 0. Okay, so it's clear that dt of chi t is 0. Moreover, we need an argument that this chi t is not trivial, if chi was not trivial. Okay. Yeah, where is that at? H is a function of chi. H is a function of small x.
So then how it is changing?
You can try to write chi t as dt of some alpha.
Right. So let's say that chi t was equal to dt of alpha tilde. Let's say. Yeah. Okay. Yeah. Good. This is as you say. Okay. So this is e to the power minus th by definition times times d of e to the power th of alpha tilde. Okay. So suppose this was the case, then chi, because alpha t is e to the power minus th of chi is equal to d of e to the power th alpha tilde. And therefore chi was not in cohomology. Thank you, Diksha. Argument's clear, right? So if this guy was trivial, the earlier guy must also have been trivial. So we see that these two cohomologies are the same. This is what Shoaib was referring to. Similarity transform preserves cohomology. But you know, Shoaib, unitary transform preserves Hamiltonian. And this is not a unitary transform. Okay? Abstractly, if you take the operator Q and do S Q S inverse, S Q S inverse does not preserve the Hamiltonian. Why not? Because Hamiltonian is Q dagger plus Q dagger Q. Now we take S Q S inverse. S star S inverse dagger Q dagger S dagger. That's just nothing nice. It's nothing nice unless S inverse S dagger is S, which is unless S was unitary. Okay? So it doesn't do anything nice to the Hamiltonian, but it does preserve cohomology, as we've just argued. Okay, we argued in the context of a particular example, but it's a very general thing. If you have two operators that are related by similarity, the same argument goes. Okay, the same argument we've used basically works. Because anyway, you can work it out, right? If you look at Q, cohomology of Q and cohomology of S, Q, S inverse, it's the same because if something was annihilated by Q, then S inverse of that thing is annihilated by this object, or S of this, and so on. The same argument, basically. Okay? Excellent. So, now we understand what the problem with the potential is as far as zero energy states are concerned. Because remember, zero energy states care only about the cohomology. So while the whole spectrum of the problem will be greatly reorganized by adding this potential, spectrum of zero energy states, form by form, form number by form number, does not change. Because the spectrum of zero energy states was the cohomology of Q. Or the cohomology of D operator, which is the same as the cohomology of the dt operator. Number of zero energy states that are P forms does not change. It's not a function of H. Now, this is a remarkable thing. This is a remarkable thing for the following reason. Let us look at our action. What is the new term in our action because we've added this? Potential. Well, we know that We know that because our action had a minus w squared by 2 in our simple model. We just have to covariantize that. Remember, w in our simple model was del I by del x. Right? When we got our simple model from a superfield, we had to take I to be the integral of w. Okay? So w was this. So the action, basically the clear, obvious covariantization is del I del Ji by 2 Gij. Okay. Right. We had this, and then there was also the term that was W sigma. Okay. Now, what about that term? That term was, the term was W prime psi chi. Okay. Also what to do here is clear, because W prime is second derivative of I. Okay. So this will become plus del I del J of I psi bar I psi J. Right. This is neither symmetric nor anti-symmetric. This is one is psi bar, one is psi. Yes. Covariant. No. Yeah. Right. Let's see. And this, as you say, is one of these will be a covariant derivative. Right. Maybe we will need to symmetrize. Anti-symmetric. Symmetrize. What? For scalar, it is symmetric. Right. So, yeah. So this is okay, right? Because psi bar psi, it's not, were you worried it was 0? It's not 0. Yeah. Okay, I'll just check though with what Witten has. He doesn't even write on the Lagrangian. Okay, so anyway, so this is these are the extra terms we needed to have in the Lagrangian. Okay, each of these terms will contribute, of course, to the Hamiltonian. But the easiest way to work out the Hamiltonian is even just to ignore the Lagrangian and just work out the commutator of Q with Q dagger. We know what Q is, we know what Q dagger is. Okay, so we know what Q is, it's e to the power minus ht d e to the power minus ht plus, and Q bar is the adjoint of that. Okay, so it's a simple exercise from this to just work out qt, q bar t plus q bar t, qt. Work it out keeping track of all terms, and I'm writing down what Witten gets, if I can find it. Yeah. He gets that the Hamiltonian dHt is equal to dd star plus d star d plus t squared del h, the whole thing squared. That's this.
And this you got from dt star plus dt star.
Yeah, from dt star plus dt star dt. That's right. That's, I've got it. But you can also get it by canonically quantizing this Lagrangian. Okay, plus t d2h by d phi I xi d phi xj, and he puts an explicit commutator here, psi I bar psi j commutator. Right? And the commutator is just what you commented on, Shuman, that we could also write it with the opposite sign. If you put the opposite sign, you get a minus sign. Okay, so both the canonical quantization or just working out dt star plus dt will give you a Hamiltonian. And this is the Hamiltonian. Okay, we are running out of time. We are out of time, but I'll just quickly make the point and stop. Sorry, I vowed not to go over time in this course, but it does. There's a T. That thing that looks like an I is a T. Oh, maybe it's an I times T. Let me check. There's definitely a T, but yeah, it's a T, just a T. Right? It's a T because every time there's one H, there's one T. There's a T square here because there's two H's, and there's a T here because there's one H. That T was just a counting parameter. Okay, let me make the main point. Let me make the main point here, and then I'll stop this. The main point is the following. Now let us take the limit t goes to infinity. In the limit t goes to infinity, okay, all these other terms are sort of irrelevant compared to these terms. This is the most relevant term because it's t squared. So what we see is we've got this huge, very steep potential proportional to t. But we know we're going to have zero energy states because we know that the number of zero energy states cannot have changed. It's the same as at t equals 0. So how could that be? That can only be if h goes to 0 somewhere, del h goes to 0 somewhere, so that this potential vanishes. Okay, so first thing we learn is that it must be that this function has critical points. Okay, that's just some statement about functions on non-trivial functions on a topologically complicated space. Okay, on a compact space basically. Okay, fine. But what we're going to get is more detailed information about these critical points. Okay, so now look, now we're back into our semi-classical world because we're doing some approximate calculation in the limit of very large t. In our semi-classical world, every time we have del h and a critical point of h, okay, an extremum of h, right? That there was an extremum of h, of course, follows, right? If it's compact space, there's somewhere where h is maximum, somewhere where h is minimum. At least one extremum had to be there. Okay, so this extremum of h, let's say there are m of them. Let's at the points x1, x2 up to xn. Now I want to know whether semi-classically we can get zero energy states from such an extreme. Okay? So the problem is as follows. Let's suppose that h, okay, let's suppose that h at its extremum has a normal expansion in terms of some coordinates. So that h is alpha 1 squared plus alpha 2 squared plus alpha 3 squared up to alpha d squared with some coefficients. Okay? I will do this properly next time, but I'm just giving you the main idea. Okay. So suppose we've got some h with some harmonic expansion around its minimum. As you know, every harmonic oscillator in many dimensions can always be turned into a bunch of decoupled harmonic oscillators. Okay, so there are various associated harmonic oscillator frequencies. And so from 0 point energy we will get the minimum energy state is T times alpha 1 by 2 plus T times alpha 2 by 2 and so on. Mod alpha 1, T times mod alpha 1 by 2 plus T times mod alpha 2 by 2 and so on. Okay? And it looks like a very high energy state. However, we've encountered the same thing before in the study of RW. And we know how that was dealt with. The positive harmonic energy oscillator state that you got from this term were cancelled by those that you got from this term. Okay? And precisely these eigenvalues that get, you see, this is the first expansion of del H. The second derivative of H is like the first expansion of del H. So the things that come here and square are the harmonic oscillator frequencies are the values that appear in this thing. Just like in our one-dimensional potential. We'll see this more carefully next.
How does the order of T match?
It matches because the ground state energy is proportional to h bar omega. Omega squared was T squared. But ground state energy was T. And in fact there's an h bar, but this also came with an h bar if you remember. It was the inherited term from the h bar, order h bar term. Sorry. So what's going to happen is that these guys here, we're going to have these number operators in the different directions. And precisely if we choose the number operator to be occupied or unoccupied, we will be able to cancel this 0 point energy. Exactly like we did in our one-dimensional problem. Whether occupied or unoccupied will depend on the sign of this object, the sign of the eigenvalues here. Now, the sign of eigenvalues tells you how many unstable directions there are away from an extrema. Okay? So, as we will see in more detail next time, the way we will get zero energy eigenstates is by occupying as many fermions here as there are unstable directions around this extrema. Now, mathematicians like to characterize extrema of functions, and they characterize them by one of the major characteristics of these extrema is the number of unstable directions. The number of unstable directions has a name for mathematicians. It's called the Morse index of the extrema. Okay? So what we've concluded is that if the extremum has Morse index P, then its zero energy state will be a P form, because the number of occupied fermions was the form degree. Okay? So associated with every Morse index P extremum, there is a P form. Now what could happen semi-classically? One thing that could happen semi-classically was that you have more states, more vacua than you're eventually going to have, and some tunneling, like the tunneling we talked about at the beginning of our class, remove some of them. That is possible. But it's impossible that you have less states, because the tunneling effects are only within the sector of very low energy states. If you didn't have the states to begin with, nothing's going to be brought down by some very high, very non-perturbative stuff. Okay? So we immediately conclude something. We can conclude that the number of extrema on a manifold with Morse index P has to be greater than or equal to the pth Betti number of that manifold. Because otherwise it could not have worked. Right? Because otherwise the number of semi-classical zero energy states would have been smaller than the number of exact zero energy states. Remember, we know the exact number of zero energy states in this problem. It's the cohomology, and therefore it's the pth Betti number. We know that, right? But semi-classically, we're getting the number of states with Morse index p, with p unstable directions, number of critical points with p unstable directions. If that number of critical points with p unstable directions was less than the full exact answer, we could never have got the right full exact answer. Because tunneling can remove states, it can't add states. Okay, and so we prove an inequality. Inequality is on a manifold with Betti number p. Remember, p is the dimension of cohomology of p forms, Betti number p. On a manifold with Betti number p, the number of critical points of Morse index p with p unstable directions has to be greater than or equal to Bp. And the remarkable thing is that for mathematicians knew this inequality when Witten wrote this paper, but it was very recent and quite regarded as a very interesting thing. But it comes out so easily from the study of supersymmetric quantum mechanics. Okay? So this is the first thing I want to tell you. Oh, it's very late. This is the first thing I want to tell you about this. The other thing was that Witten then studies, if you've got this set of states with Betti number with Morse index p, he then studies the instant terms in this space and tries to see how many of them can be lifted or not. Even that is quite cool and of some interest. So I'll tell you a little bit about both these things tomorrow. Maybe 2 or 3 more lectures for quantum mechanics itself, and then then we move to field theory. Okay, that's it for my class. Any questions?
So you showed that the cohomology of d and dt are same, and the isomorphism map was multiplication by e power minus ht, and we are taking t tends to infinity. You only commented about the critical points of h, that is del h being 0, not h0. So in the limit t tends to infinity, e power minus th will become 0. So the isomorphism map will be 0. So the cohomology of dt seems to be shrinking to 0.
Yeah. So what we want to do is this. We're imagining that t is very large but not infinity. And what we're doing is computing the energies of our states in an asymptotic expansion in t. Okay? So let's see. So good question. Suppose we've got a state where the energy of these two are not cancelling. Then all such states have energies of order t. Okay? Such states can never become zero. It can never become zero energy states. To make this argument, we didn't need t to be infinity. We just needed to be sufficiently large. So the shrinking doesn't have to worry you. You see, it's sort of in the limit. And the limit is taken from finite t. But more precisely, so Witten words it very precisely. He words it as computing the energies of states in an asymptotic expansion in t. And you want, in that asymptotic expansion, for supersymmetric states, the energy has to be 0. But any state that has t in it, clearly it's not going to work. Any state that has 1 in it, also clearly it's not going to work. Now, if you've got a state with order t term is 0, order 1 term is 0, order 1 over t is non-zero, then maybe it works, maybe it doesn't work, then you don't know. Right? But you can definitely say that there have to be at least as many states as the Betti number whose energy in an asymptotic expansion in t has no terms of order t and no terms of order 1. Right? And to make this argument, t has not been taken to infinity, it's just very large. Okay, but excellent question.
How do we maintain the order 1 term to be 0?
How do we maintain what?
That the term with order 1 will be 0.
How do we maintain that the terms with order 1 are going to be 0? Yeah. So that now is perturbation theory. Right. That is perturbation theory that has to be done carefully. But since all we are doing at the moment is getting an inequality, okay, the fact that we have not done that doesn't bother us, because nothing that we say there can change it, because at least the states with order t, with less than order t, those number of states have to be less than the number of the Betti number. However, in the next class we will do better. Okay, we will do better. It's the same argument as before. You see, the argument is going to be that because in the end the number of states depends on the whole manifold, on the topology of the manifold, it cannot be sensitive to local variations. So if I change H in a way that is not changing some topological feature of it, that will not change the answer. So this is already an indication that perturbatively you are not going to get corrections. But non-perturbatively you might, because you might have tunneling from one state to another state, very similar to the problem that we dealt with at the beginning of the class. So let me remind you how to put that. In this problem, the total number of actual ground states only depended on the topology of this function. How many times it crossed the surface? Okay? Because of that, if I wiggled this thing about in a single valued way, if I wiggle this around here, it cannot change the answer. Okay? Perturbation theory sees these wiggles. Non-perturbatively you see whether there is another minimum or not. That will be the basic reason. But also an excellent question. Other questions? Sorry people, I will try to avoid going so far over time next time. Okay, so next time.